you guys hear me? Sure. Thank you. I think I'll have to start. Hi. Can you hear me now, Salman? Yeah, it's good. Thank you. Thank you. Thank you. Let me just. Okay. Good afternoon. The topic. Okay. Good afternoon. The topic that today I'm going to be presenting is the image artifact in mobile computational photography. And this whole presentation is about what sort of a pictures that we capture in our mobile phone. Either these are the real pictures or it is just a composite of multiple pictures or frames that we have captured. I'll go around with that, like what is the current mobile phone pipelines that has been developed and what sort of a problems that it has and how we can measure those and what are the limitations that still exist in these models and everything. This is pipelines. The first I'll explain about the computational photography paradigm. Then I'll delve into the ghosting artifacts. What are the challenges? What are its anatomy, the characteristics, and everything. Then what are the current data sets that has been published? What are their gaps? What are the limitations of those data sets and how it is not suitable for the current pipelines that has been used for the specifically talking about the mobile photography. And then the dataset that I have been published in the mobile ghosting artifact imaging dataset, MGAD, and how it is more suitable and more appropriate if anyone wants to do research in mobile photography and mobile imaging. Artifact detection with the difference map networks, artifact removal, and so on and so forth. What are the transformer models that has been proposed? And lastly, the future direction and the conclusion. Talking about the computational photography paradigm, from burst capture to the perceptually coherent image or the photograph that we have. All the photos that we capture nowadays in our mobile phones is not just consist of just one frame or one picture. It is not a single photograph that we captured. Be it may Samsung, Apple, or the Google smartphones or the Pixels, they capture the multiple, you can say, burst of the phones in which they have captured like multiple frames and then computationally merge them to generate a one composite coherent pictures. They use this sort of a technique to overcome the limitations of mobile camera sensors because mobile camera sensors are just 8 bits while the DSLR or the bigger camera phones, they have like 14 bits of raw imaging photographs. So this camera revolution is just a software revolution, not the hardware one if we talk about in terms of mobile phones. The most famous platforms or the most commonly used mobile phones are the Google Pixel, that use Google HDR+, Apple Deep Fusion, it is only included in the Apple Pro series, and the Samsung Nitography. These are the famous ones that has been adopted in like Samsung Ultra series. These mobile phones, if we talk about in terms of Google HDR, they capture between from 2 to 15 frames and then do a pixel binding. The pixel binding is when they capture these bursts, how much pixels accumulate to make one pixel in the final photograph. So the ratio of that will become like 4:1. So the 50 megapixel camera sensor has been collapsed into just a 12.5 megapixel of the final output that we get. While in the case of Apple Deep Fusion, they are very much precise and they only capture like 9 frames. And the pixel binding ratio is 4:1. So their 48 megapixel camera sensor has delved into or the collapse into the just 12 megapixel. While in the case of Samsung Nitography, they have like 200 megapixel camera sensors. So it will delve into like 12.5 and they use from 2 to 30 frames. It depends upon the night version or the night vision, how much darkness, how much low light it is. The higher the rate of the, or you can say the lower the light in the environment, the higher the frame that it will capture. So the pixel ratio is from 4 to take like 9, in which the binding will all along that happens. The goal of these is to achieve a perceptually superior results across different lighting conditions. If I'll talk about then the multi-frame fusion pipelines, in which, as I explained, like multiple frames have been captured, and across the underexposed or varying exposure scenarios in which we can capture on the short term, normal, or the long exposure to capture in the burst real environment. Then the alignment optical flow pipeline in that the second frame is in which there's a reference frame has been selected. Different camera has been selected, like in Samsung they select 2 frames and then they merge and generate a one composite medium exposure. While in case of Apple they select only 1 frame in which they just selected a medium exposure frame, and all the images, the reference images, the burst images are aligned in that way. So they align all the frames in that sort of a way. Then HDR fusion, in which all the movements and the denoisification has been occurred. Lastly, the image signal processor, the ISP, performed tone mapping, local sharpening, and the noise suspension to generate the final coherent image in which all the images, all the lights, everything has been aligned in that way. But what happens if the alignment optical flow has been collapses? Or what happens if the HDR fusion or the denoise occurs? First, the alignment optical flow is like if there is a sudden movement in that way. Like you are capturing motion or you're capturing a picture in the static motion, yes, then the image will be generated, might be good. But not all the images or not all the pictures that we capture in the real time environment are in the static motion. If you are capturing motion, or if you are capturing a picture of a football match, or a capturing motion of a road in that like cars are moving or a person is walking. So the motion of that person or a car might not be same, or the position of that might not be same during that static during that burst mode. Because car might be moving along the way, so that might create an alignment issue. And when that sort of a thing happens, the sub-pixel displacement during these frames generates some sort of a ghost among those pictures. And this results in the displacement map carrier residual in the merge step. And that generates a translucent while double contours in the moving edge, in which we see a pattern that is following that car. While the other scenario is like if there is a fusion conflict, like some sort of a light changings that has occurred. Like in the one when the burst mode is capturing of like 30 frames or 10 frames, there might be a shadow that occurred during that phase. That sudden exposure change of the image or the sensor that we have, that can generate to the fusion and stable averaging, producing halos or the blurry edges or the low frequency ghosting blobs. Like, and I'll explain what the ghosting, like the low frequency ghosting blobs in much more detail in the end. I'll show you with an example. So these sort of a misalignment and the fusion conflicts, or these sort of a collapse or the failure of the fusion pipeline, generate ghosting artifacts, and those are the translucent display duplicates, blurry edges, some sort of a subtle but very visible patterns that aren't even in the images, and the temporal inconsistency that degrades the overall image quality. If we talk about those artifacts, the colors that are in the red are the high frequency, in which that occurs when due to the misplacement or misalignment during that optical flow occurs, while in the green one are the visible that the low frequency occurs that has happened due to this sort of a movement. While the first picture is just specifically about the high frequency artifact and the second one is the low frequency, while in some cases when we are merging multiple pictures and multiple frames, there might be a scenario in which both of these artifacts are occurring concurrently, and that is the case that happens. And the last picture, if you look at that specific part, although the person is here, but due to the sudden misalignment or you can say the movement of that, we see a shadow of that person here. It's not a ghost, yes? Yeah. No. One of the reason of that is it's all about the camera dependent or the user dependent. The hand movement, the current models of the or the current systems like pipelines like Samsung and Apple, they have adjusted to that. Like Apple Cinematic Pro, it adjusts that because it captures that much of an information, and the movement stabilizer in which they use a movement flow that can take care of that. But the problem is that like if a person is taking about like too rapid movement, then that will happen.
Is it it's that in the case of videos, right? While what about while taking photos?
Yeah.
Like if it's I'm taking photo and something that does but then the movement is like that.
Yeah, then obviously then it will take care of it. Then it will happen because in videos you are taking 30 or 50 frame per second,
Yeah.
while in the case of picture you are only at max capturing like 30 frames, and only in the case of night mode when you just want to capture as much in a light as you can. While in the, let's just say, take for the example of iPhone. In iPhone you have a static standard rate of 9 frames for even one image. So in 9 images, you cannot predict or that much of a motion, and you cannot compare it with a 30 or a 60 frame per second. Because with 60 frame per second, you have a very much in-depth information of the movement, be it a person or a car or whatever case scenario that happens. Yeah. Okay. So why ghosting artifact is the hardest one? The problem with that is like although we have seen like we have multiple ghosting artifacts that are occurring even in the same image, or if we talk about that. So why ghosting artifact is that much harder? The first problem is that it is content dependent. It is not about that. And here the answer is of your question. Like static backgrounds, with a static background, and if everyone stands still, the images that we have are one of the greatest one, or that are might look aesthetically good and that are very perceptually well, but that does not happen in everyday world, like real world scenarios. So the motion between the frames, that can be abrupt, and that cannot be homogeneous, and that can be, you cannot say uniform. It can be of any sort. So with that, the camera is not, the hardware is not the problem, it's the environment or the content that you're taking the picture of. The second one is spatially varying. Ghosting artifact or even the artifacts, they do not occur or they do not happen in the whole picture. Like if we have like 100 cross 100 sort of a pixel information, that's become like 10,000. Yeah. So in that, there's only might be 10% pixels or 10% of pixels that have that sort of a problem. So when we are carrying or when we are detecting, be it PSNR or that, so we only have to focus that specific area, because the overall PSNR of that specific image might be good, but the ghosting artifact still cannot be addressed, and that is much of sort of a pixel level localization that we need. We need such sort of a system that in which we can do special sort of engineering, image in painting or that sort that can be do on the pixel level, in which we need to detect and then replace or update or remove whatever the ghosting artifact that we can. The second is the frequency diversity. In ghosting artifacts, like we have a two different type of ghosting artifact. The first one is the high frequency and the second one is the low frequency. First, the high frequency artifacts cover only, I don't know whether it's that much visible, is all about the blurry thing that shows that an object has some sort of a past or following some sort of a thing. While in terms of low frequency artifacts, we see some sort of weird patterns along the way. We see some sort of a lines that aren't even there. So this diversity needs some sort of a model that can address both of these things, because both of these things require different sort of a strategies and that are entirely different in terms of addressing it. And the last one is the perceptually subjective. A thing that might be a ghosting artifact, the highest ghosting artifact for one sort of a person might be just a natural blurring or a mild ghosting artifact in that way. So this perceptually subjective of ranking or the criteria of the ghosting artifacts or even artifacts is only about that makes a little bit problem much more tougher or much more harder to address. The gap, what sort of a data sets or what sort of information that we have. Yeah,
One question, like
yeah, yeah,
all these pipelines,
yeah, yeah.
they only focus on the fidelity part, right? In a sense that, like for example,
LPIPs?
yeah,
No.
like they only focus on the PSNR thing or the LPIP.
They focus on both of these things. Even with the one of the major criteria is PSNR and SSIM. But the issue with both of these things, and I have a slide regarding that. PSNR is all about the global aspect of the picture. They do not consider that, like, if we have to talk about it, and let's just assume only this block is a ghosting artifact. And if we consider all these of this, like we have a 2/3 of a picture that is in the or 3/4 of a picture that is of the good quality. So we have the PSNR output ratio might be good. But if we talk about SSIM, we have a 75% of a ghosting of a good quality picture. But in reality, we have a ghosting artifact on that specific block that isn't addressed. While in terms of LPIPs again, it's about the global thing, the perceptual impact of that picture. It's again the problem that still exists. We are working on the parameters that do not address or that do not take care of what the underlying problem is.
My question is that for instance, we have some patterns here on the wall.
Yeah, yeah. Let's just consider this specially varying
So
section.
yeah, so the thing is like for example, if I take a picture,
Yeah, yeah,
can I be sure that it is capturing the 100% of the real world content? It is not adding to make it perceptually better.
yeah,
Some artifact.
yeah,
Because like in different models we had artifact.
yeah.
It's not evident from the blind eye, but if you focus on the details, you will find that in reality the real world is different, the picture is different.
Pro.
So
The thing is, you are already asking questions that I have in the slides in the last. This is my second last slide in which I address that. Okay. The gap. These are the good questions, but I have already that in the slides. The gaps where the prior artifacts or art fails. There are I divided into two parts: the traditional approaches that are pre to 2017, in which the most of the work that has been done is the pixel-wise difference thresholding, in which they talk about or they have done on the pixel level thresholding. But the problem is that it is the manual threshold. It is not the adaptive one that changed with from picture to picture or the overall scenario. And the secondly is that they have to perform the consistent optical flow checks and the motion segmentation. They fail to address the subtle low frequency artifacts that requires manual threshold tuning per sequence. The problem with that, the low frequency artifacts, it is just again the same scenario that you have said. Like, overall picture looks good, but it generates some sort of a patterns that aren't even in the picture. So that is the problem that traditional approaches that fail to address, in which they use some sort of a ML techniques that they have done. While the post 2017, like in the CNN-based classifiers or attention-guided networks or transformer-based method, they have tried to address these problems on the basis of that, in which we feed them transformers or do some image painting that are better at learning artifacts pattern. But the problem with them is all of these methods are trained on the DSLR datasets. They do not represent the mobile coordination conditions. And due to that sort of a problem, these models were trained on the DSLR cameras or DSLR datasets. And the second one is all of them do not consider like the handheld mobile phones. They were designed on they were developed on the tripod, in which the camera is always static, the background is always static. So that is the one problem. The second one, the different sensor characteristics. While mobile phone have only 8-bit of a sensor information that it can capture, while the DSLR have the 14-bit of a sensor captures. They have different image signal processing unit, ISPs, pipelines, and have a different artifact patterns that occurs. While in DSLR, you can generate natural blur or the already you can say motion blur itself. But for mobile phone camera, it's a blurry thing that they try to remove it as it can. So model trained on DSLR cannot be domain transferred on the mobile phone scenarios. So the critical gap is, or the critical prop question is, we need a mobile specific ghosting artifact dataset. Sorry. That with a patch level annotation, and it has a multi-device diversity in which we can use a multiple devices to generate that sort of a thing. And it will address or it will provide some sort of a thing in which we can work on high frequency as well as the low frequency. And no such dataset has been designed or developed. Talking about the datasets, the first ever dataset that has been proposed by the Kalantri in which they have used DSLR and have a specific one resolution of 1350 to 900, and they have only provided like 89 images. The problem is it is not for mobile, and it is only used or developed using the tripod. The second one, again, second and third one is on the DSLR cameras. The problem again, in terms of torsion, there is no ground truth. We can only use that for the qualitative evaluation only. While in the Parbarkar case, they have provided pairs, but it is in the controlled lab environment, not in the real world. The first ever mobile phone dataset for the denoising and the ghosting artifact, it has been proposed or presented in CVPR 2023, in which they only use one mobile device, that is Oppo, but the size of that dataset is just 281 images, and it provides frames in which you can compare to denoise that image, and you can have as much information as you can. But the small scalability of it, the lack of device heterogeneity, and that sort of a problems make it much more difficult. To address that, we developed or designed a dataset, Mobile Ghosting Artifact Imaging Dataset, or MGAD, in which we developed it on using the Heman ICIP paper. We use that sort of a pipeline as in which they have proposed a real-time video denoising for mobile phones, and we developed or built our own pipeline on the basis or on the structures of that. It was a cornerstone in which we used two frames, frame T and frame T minus 1, and we use generator Gaussian pyramids for the multi-scalability to reduce the resolution of motion analysis, and on that basis we generate the Laplacian pyramids. The usage of Laplacian is to isolate frequency. If we have a control over frequency, we can generate as much artifacts with the weight of with the use of our weights, so that we can generate as severe artifacts and as well as the subtle artifacts. Laplacian provides us that sort of information, plus we can generate for the high frequency artifact and as well as the low frequency artifact. While we use those Gaussian pyramids, we align and displacement map, we merge them, and we merge the displacement of the Laplacian with the control weights to generate a pyramid collapse and generate the frame T. This is the simple pipeline of the baseline paper. What we did, we collapsed at that specific stage. We used to control the artifacts, and we displace map using the Laplacian pyramids to generate those artifacts. The motion between frames, you can say disturb and disturb them or disrupt them to generate those artifacts, and generate ghosting artifacts in dynamic region, not just of the one specific part or one specific regions. Due to that, we able to generate ghosting artifacts in that sort of a way. As you can see, so even in that scenario, although this person has both of hands, but it's only, you can say, avoid all of them, while in that case, you can see there is a mismatch or there is a generation of ghosting artifact of a very high frequency. Yeah. Later on, as we have discussed, the most of these data sets, while the prior data set, even in our data set, while if we generate those artifacts, that's a one thing. But for a system, it needs, you can say, a patch level annotation, a pixel-wise annotation where that specific ghosting artifact is, so that we can teach or we can guide model to focus on those parts that have that specific artifacts. For that specific thing, we developed or we designed a patch level ghosting artifact labeling system, in which each image is decomposed into an overlapping patch size of 2 to 4 cross 2 to 4, and we use a 0 to 5 range, in which 0 means the image is or that specific part is clean, while the 5 means it is severely ghosting artifacts. All the annotators have been given 3 images when they have focused on that: original, denoise, and the difference. While the usage of, you can say that this trifecta or triplet image is that while sometimes we might not be able to see or clearly visible those artifacts. So the difference between original and the denoise or the final output images, it highlights those, okay, these are the differences and how far it is, how much error it has, so that when a person who is annotating those things, he can have a better understanding of how that specific region or how much sort of information has been disrupted from original to the denoise part. And this entangled that true ghosting from the compression noise and the motion blur that happens during that sort of a image processing way. Why? Because unlike prior datasets, we have addressed the high frequency, we have addressed the low frequency, and we have designed a system that can be done on that specific parts. So due to that, we have, if an image is just a noisy part, but it is same in terms of original and the denoise or the final output image, it will be marked as 0. While if the image has some sort of a ghosting artifact, we can highlight that, okay, this specific part has a 4 frequency from the annotator level, like it is subjective from person to person or from the perspective of an annotator, while in other case scenarios, we can highlight, okay, this has a much higher accuracy and this might have the much different accuracy. These annotations are not good. I just designed it like last night, so don't focus on the annotation part. Specifically, I just randomly put the numbers. But this just gives you an idea how to address or how we have designed that system specifically. To it end, we have lead to like 2,520 images, in which 1,060 images are for the high frequency and 1,460 for the low frequency. Furthermore, apart from these 1,060, it is not just the RGB images. Among them, 530 images are the raw images that that camera generates normally. Because camera did not work on the RGB, it performs on the YUV 420, YUV 424. So we have a raw images of 530 and 530 for the RGB. While in case of low frequency, we have like 730 in terms of raw images and 730 in case of the low frequency. We have used like multiple devices. We have used iPhone from 6 to iPhone 14. Samsung 20 Plus and the GoPro for the device heterogeneity or using multiple devices. We have used 87 different scenarios in which a static person with the background moving or a background static with the person moving, night, day, and that sort of a scenarios. And we have annotated total 101,418 patches, to be very exact and precisely speaking. Now comes, although we have developed a data set and everything, how model or the current work performs when we talk about artifact detection and the removal, from a patch level localization to the transformer level method. For that, we have developed this sort of a very simplest pipeline in which we use original frames as the ground truth and as well as the denoise frame, and we divided them into the 2 to 4 cross 2 to 4 patch size. So each patch size has been used a difference map. So we calculate a difference map in DUMS, difference and the absolute difference map, and we forward that model 3 different things. The original patch size, denoise patch size, along with the difference map. So the model will have a better understanding of what sort of a noise or what sort of a difference or the artifacts that it is dealing with. We train the model on it, and then we use just a binary output, whether it's a ghosting artifact is there or not. So these difference map perform that sort of a enabling, especially you can say spatial localization rather than coarse image level detection. We don't want to say, okay, this model has ghosting artifact, this model has that sort of a PSNR, but it provides us, okay, this patch has specific. So then we can map and along the way to the, you can say reverse engineering in that way, we could connect all those patch and we can say, okay, these specific patches have ghosting artifact, while these does not have that ghosting artifact. We use simple CNN and the DNN in which we use absolute difference and the difference map to generate that. And we use class weights in which to enable, since as I told you, like there's a not all the pictures, especially varying part. Every picture does not, all the picture, all over the pixels are not the ghosting artifact. There are very specific regions that have that. So since that problems creates that, we do not have all the pixels have that. So the pixels with the non-ghosting artifacts are much higher as compared to the ghosting artifact. So we use class weights, and we find that even if we do not use class weights, but with a difference map, in which pixels shows that, okay, that much of a change has been occurred in that specific part. So we have achieved like in terms of accuracy of 95.82 and so on and so forth. While with the difference map with Go class weights, the overall ghosting artifact detection has been 95.88% in terms of that. These are the parts in which we use the removal things, in which we use DNCNN, block CNN, like artifact removal control net, and the fast ARCNN to remove that. And now comes your question about the PSNR, everything. Although you can see that DNCNN leads in the PSNR in all the case scenarios, like be it with the low frequency or the high frequency, it has a 30.77 with the SSIM of 86, while ARCNN has a SSIM of 91 and 92 for high frequency and for low frequency and the high frequency respectively. But the problem is that those larger strides, like in terms of fast CNN, does not have that much of a high PSNR, and that's why overall the PSNR of that image might be improved or of that can be enhanced. But the PSNR, the problem with that, it is the average error globally, not the locally. That's what I was like, why PSNR and SM are not insufficient. The PSNIR misses especially localized ghosting artifacts. It does not focus or it does not highlight that specific part. SSIM captures on the basis of structural integrity. They do not, you can say, focus on the semantic wrongness that has been occurred. Like be it whether it's a ghost or object, it match how much pixel similarity between those images of the original and the denoises. While the LPIPS, it correlates a perceptual quality of the image, but not trained on the ghosting distortion. It can always tell you about, okay, that image has been LPIPS of that much, but if it is a ghosting artifact, it might be the low frequency in which you can see a lot of lines and patterns that are very, very subtle. But LPIPS or the PSN or SIM can be as similar as it can be. No existing matrix distinguishes ghosting artifacts from natural blur, and that is one of the problem that why PSNR, SSIM, LPIPS are not the problem that can address those specific issues. Again, coming back to the why ghosting artifact is still harder than denoising, or why the ghosting artifact is a challenging thing. In case of denoising, the removal of random permutation from the signals is much easier, because denoising means that we have to remove that noise of that has been just induced or that has come along with due to the environment. But the problem with the denoising is the more you denoise the image, the more artifact it will be happening. We have to maintain a balance, because noise is secondly, noise is independent from the scene content. It is happening due to some sort of a camera blur or that sort of a thing. While ghosting artifact is a content dependent thing. It happens due to the picture that you are taking, the content that you are collecting. That's why, because it can generate like translucent or edges or the blurry thing or some sort of a ghost or some sort of artifacts, lines and that sort of a thing. There are two possibilities in which we can go, and that is an open-ended problem. The first is detect then remove. First we detect those artifacts and then we remove. It's a two-stage method. It can be interpretable, it can preserve the clean region, but the problem is error propagation. If our model or our method make detection error, it says that that part has the artifact, but it doesn't. It relays to the removal part, so we might remove those clean, right images or patches that do not have. The second one is a single end-to-end network. But the problem with that, it might not be suitable for the mobile, because it needs much more resources, as that might not be suitable for the computationally, mobile-wise computationally speaking. Moving on, the second is like the hint paper has been proposed in the IEEE transaction of multimedia in 2024, in which they propose a mask-aware encoding explicit condition for network artifact boundary maps, in which they generate masks for those artifact region and try to in-paint them. They train that model in that way so that it can remove those artifacts parts that has been occurred. So since we have some sort of a patches that can define, okay, this patch have a ghosting artifact, so try to remove or try to reduce that, So they propose an idea to just replace those parts or replace those sections that has a masking, using a mask, in which we try to do that. So in which they use multi-scale skip connections to retain fine-grained edge information, then scale single in-painter discarding during downsampling, and they try to generate that sort of information in which they use masking to train and just remove or just replace those pixels that these masks covered. So that's why they have done that. We have tried to do that. Although it is the best results that we have in terms of PSNR, the PSNR was 35 and the SSIM was 97, but it is too heavy and too computationally costly if we talk about the specifically mobile wise speaking. Yes, it is good for the high resources like on the SIM system or that sort of a model, but at that time we found out that these are not suitable to deploy on the devices because the size of that model is like more than 80 million parameters, and the requirement of that project was to make a model that has like less than 2 million or maybe at max like 3 million. So the difference of that make it unsuitable to deploy it on the mobile devices. This is one of the example, and the second problem with that it is not consistent. Although this has like in some case scenarios, because the hint is trained on the generic data set, so they are not very well performed in terms of all along the way. In some cases, yes, it has a very good results. Like if you guys can be able to see, there is a specific line that I highlighted from here. It has removed that, but in case of this part, in which we have specifically highlighted that mask, okay, you can remove from there, but it still did not able to address that because it cannot model the stochastic drop down, and the ISP condition for the ghosting patterns are only specific, not specifically for the mobile. And the attention mechanism is scene sensitive, not the artifact. It talk about overall aesthetic or overall the global aspect of the picture, not just specifically for the ghosting artifacts. Yes, in some cases it performed good, but it did not show any consistency along the way. But yes, you can say it achieved the highest PSNR and everything. The second one is the real-time intermediate flow estimation for video frame, and we try to modify it for the specifically for the mobile and specifically for the images. It is a neural network-based frame interpolation in which you use the teacher-student method to generate smooth intermediate frames between the existing videos. So the thing is, like, if you have a patch or if you have an artifact, you try to use that and use the motion flow to generate intermediate frames. So the motion or the transition between that specific two frames will become consistent. So you can say 30 frame FPS video will become like 40 or 45. So the motion, after becoming motion so consistent, so the blurriness and the ghosting artifact will become reduced. And we try to address that for specifically for our problem by using that, in which we use 2 frames of original n and n plus 1, in which we use this as a blank frame, and we try to address it to the RIFE, and the RIFE use the interpolated frame, and then we try to merge or train those detection method like CNN, VGG to generate that sort of results in which we pass all these things. Furthermore, we have also explored it on the ARCNN, fast ARCNN, DMCNN, in which we frame that sort of a thing. Okay, now we will give you like interpolated frame, we give you the difference map, and we give you the original frames, and try to reduce or try to generate a frame with a skip frame interpolation to generate that. The problem with that is optical flow estimation in region with the largest displacement vectors, they fails. Although it has no hand, but the moment it generated, there are very, very minute pixels that it generated. In case of here, we do not have that much of artifact, but it adds some sort of artifacts in that region. In case of here, there weren't any low frequency artifact, but when we try to develop using RIFE, it introduced some sort of artifacts because of the patches or the lines that has been clearly visible in that sort of a thing. So these ambiguity cause the problem in terms of RIFE. And lastly, your question. Ghosting removal method trained on those erasing translucent duplicates can erase legitimate frames. It does not know if a picture have some sort of a patterns and we gave it to the model. So how do we know that, how do our model know, okay, that is a picture that we want? Just a shadow, it's just a motion blur that we induced ourselves. We want that sort of a aesthetically, or we want that sort of a thing to highlight. So how does model know where enhancement become fabrication? Where model is making those images that never existed physically in the first place. Where model try to improve, okay, this is the artifact, let me just remove it. But it didn't knew that we want that sort of a thing. There's no loss function that can, you can say, differentiate between perceptually wrongness and the perceptual correctness. How does model know, okay, this is what the user or the person who take that image has wanted that in that sort of a way? The second is there is no ghost specific perceptual loss. We need to have a system, or we need to have some sort of a loss function that distinguish translucency between the legitimate partially occlusion that happens. While the diffusion models conditioned with ISP parameters such as pixel binding and exposure index can generate artifact-free completions of that sort of image. There are very, like I think so, one or two papers that have just come in which they have tried to propose that sort of an idea. Lastly, MGAT, the first data, it's the first data set that is a mobile native, that have a patch level annotation, and in terms of isolating high frequency and the low frequency ghosting artifact across the heterogeneous data. It is the second data set in terms of mobile specificity. The first one is the LU, but that is only for the one device. We are the one in which we use like more than 9 devices in terms of iPhones, Samsung, and the GoPro. For that sort of a thing, we have done like collected like 87 plus different scenarios, and with more than like 9 or 10 different resolutions. And we address that DSLR to mobile domain gap individually that hasn't been addressed before 2023. The transformer based methods although achieve high removal quality, but they are very scene sensitive, not the artifact sensitive. We need such sort of a model or such sort of a framework that are artifact sensitive. It can be a high frequency, it can be a low frequency, but we need that sort of a system. The second thing is, although hint that has achieved a 35 plus sort of a PSNR, but we need that sort of a system that are lightweight and that can be deployable. They have a 80 million plus parameters that are not suitable for mobile low computation. PSNR and SSIM are fundamentally good evaluation metrics, but not in case of ghosting artifacts. Ghosting artifacts requires such sort of a method that can localize that sort of a thing, that can work on that specific parameters, or that can work on artifact specific perceptual metrics that can address that sort of a thing. PSNR is a global metric, SSIM is a global metric, LPIPS is the global metric that talk about the whole picture globally. We need such sort of a parametrics that can work on the localized pixel level, fine grained values in that sort of a way. This is it. Thank you very much. You have a question, Salman.
So let's go back to the initial paragraph.
Which one?
Initial paragraph. So all this, like all these models and all the solutions that you have developed, where do they fit and which alignment optical flow, HDR, Vision and Learning, which steps they basically replace?
Okay, if you talk about AR-CNN and fast AR-CNN, they have only worked on the HDR feature, while the DM-CNN and DN-CNN, they work on the alignment optical flow. So it's all about the different perspective. Like some says, okay, if we work on the HDR flows and the fusions, so we can reduce the compression. By reducing, they means that okay, if we generate that, we can remove that. While AR-CNN and that fast AR-CNN or the removal method, they said if we work on that specific alignment optical flow in which we merge or pick the best reference image, then we can combine those images all together to generate that sort of a way. It should be less than 100 milliseconds.
So, like, are they deploying the AI-based approaches for these sort of things, or still relying on traditional mathematical models?
I can't go that much into the detail, but I can say for that, like the latency is like less than 100 milliseconds due to the project constraints. Sorry. Yeah.
Okay, so ghost effect is kind of like a content-based whatever. So my question is from my system. So in one model research,
Yeah.
we use vision model. So
Yes.
let's say we want to go from this state to this state.
Yeah.
And when we're moving from one state to another, say one model using vision model to one state to another, there is some artifact.
Yeah.
So that is a sort of, if you want to classify it might be like content-based artifact, you can.
In terms of mobile imaging, artifact, or specifically, it means one thing that isn't there in the picture, but it is in our mobile.
Okay, so
Like if I take a picture and all of you are here, it's good. But if I see some people here, it's a right situation for me.
So when I say artifact is what I mean is like there might be some structural similarity of hands, or there is some movement of
Yeah.
like the object moves from one to another. So do you think to make the world model pattern which I was saying to go from one side to another, this kind of method could be transferable, or if it is transferable, how do you think we should approach it?
Bro, about the world models from the yes, if
Think
you,
about vision models. Let's
yeah,
think about
diffusion models are good, but again the problem is like whether they can be able to get those intrinsic data values that we have. Can they be that good in that sort of a way? Can they, like in terms of that, like image, if we talk about the image perspective only, like they can remove some sort of a high frequency, but what about the low frequency? Low frequencies are just the lines and everything that happens. Diffusion models, yes, we have to train diffusion model in that way, but the problem is most of the diffusion models are trained on the generic datasets or the generic information. They do not have those ghost artifact specific information. Yes, if they have, and if we fine tune or update with them with that sort of information, we can, you can say, overall the accuracy or the overall performance of diffusion model can increase in terms of world model or in terms of every scenarios. Any other question? Yeah.
How you used to measure the latency? Like, because you are working on the GPU and the end device mobile.
Yeah, in
How you used to measure?
we have a specific set of a system provided by the company in which we have to deploy, and we have to measure how much response, and the with their specific datasets in which we have to measure, okay, what sort of a time, what sort of a accuracy, what sort of LPIPS time we have collected from. The results, let me just make, these results are on the datasets that provided by them, not on our. So that's why that's the problem. Like this is those images. This is the what we have collected. This is from them.
Data field is private.
Yes. I'll much more private.
How many images were there? And
From R or from there?
from there?
They provided us videos, 10 to 15, and from that, and the images were from like 500.
You just have to test on them, right? No
Yes.
process.
On their system, everything. Nothing. Any other question? Professor, I haven't found any. Professor, because VLMs are computationally not very good for the mobile. There has been, but I have found it like last week. but it's on the archive. I'll share the link.
But I mean, what's their motivation for
They,
using the VR in this?
Professor, they did not address that specific ghosting artifact. They have only addressed like artifacts compression and artifact removal. And the problem again with that is like this paper, like Hint and the Rife paper has been published in ECB 2022, in which they address that sort of a thing, like image in painting, like Facebook SAM and everything. Like you can paint and you can draw lines and it can remove that sort of a thing. There's a paper that is published in like Llama, yeah, the Llama large artifact mask removal thing, in which they use a larger mask to train model on that. They use specific mask and they just post it on the images and then they train model, okay, try to predict that, try to predict that. So with that training of supervised learning, in which they teach on that, like okay, how far you are and how close you are. So they use that to remove the artifacts.
So, I mean, from what, in what aspect they are working to increase the
PSNR.
I mean, why they seem, why they are motivated to use LLM or VR in this?
To generate more images that are as much aligned or as much close, like it is just like a diffusion model, how much close image or how much accurate image that you can generate from that.
Related to the generalization of VR or
No, it is just specifically for the image generation, like diffusion models are like the celebrity datasets that we have, the SLEP, in which you use the mask to cover their faces of famous celebrities, and then you give it to the model, and model try to fill those patches and try to fill those images. So it can be a image of Salman converted into image of Saim or some way. So that was. Any other questions, guys?
if there's no more questions, then let's finish here.
Thank you. Thank you. Thank you.